Assalamu alaikum. Dear learners, I hope you are fine and have watched especially the previous video in which we discussed what robot dynamics are and ultimately what is the need for a robot controller. Just to recap a bit, this was what we produced in the previous video. We used inverse dynamics of robot to get torques required for movement on our desired trajectory. Then we fed those torque to the forward dynamics of the robot that will take in the joint torques and will give us the joint accelerations and ultimately joint positions. These joint positions should ideally be equal to the joint positions corresponding to our required trajectory, and we saw that they were in fact equal. However, when the same torques were provided to a physically modeled robot, that robot didn't follow our desired trajectory. This was because of the fact that the inverse dynamics block used an ideal robot model which was somehow a bit different than the physical robot model, and because of this difference, the torque required for moving the physical robot should be a bit different as well. These graphs over here shows what was our desired trajectory, what trajectory forward dynamics block generated, and on which trajectory our robot moved. We can clearly see the differences between the desired and the followed trajectory in case of a physical robot model. Here comes the topic of today's video, that is controller. A controller will be a system that will generate torques suitable for a physical robot model so that it may move on our required trajectory. In this video, I'll discuss only one type of controller, that is PID controller, which is extensively used for this purpose. However, another kind of controller, that is computed torque controller, shall be a topic of my next video. So here are the things that we are going to learn today. First of all, very quickly, we will discuss what is an independent joint control and a typical control system. Then we will talk about control system considerations for robotic manipulators, and we'll see what feed-forward compensator is and why it is required. After that, I'll quickly introduce PID controller and then move on to MATLAB for implementation of the discussed control schemes. However, implementation of PID controller requires tuning or selection of at least three parameters. And I've used a word at least here because in our case, these parameters are going to be 6 for each joint. Therefore, for a 3 degree of freedom manipulator, we have to select 18 parameters, which is impossible to do manually. Therefore, we will learn how to use MATLAB's control system optimization method to automatically tune all the parameters. So dear learners, there are basically two types of controls for robots. First one is an independent joint control, in which we treat each joint as a separate independent system. And in the second one, we treat complete robot as one system and try to control all joints through a single multi-input, multi-output controller. For this video, we are going to discuss independent joint control. We are going to have a separate controller for each joint. So in the shown typical block diagram of a control system, the controller has in fact a combination of n controllers for n degree of freedom robotic manipulator. The example which we are going to use will be of a 3 degree of freedom non-planar manipulator. Therefore, we will be having three separate controllers which will generate three torques for the three joints. So the overall scheme in any control system is to take in the reference trajectory or the input, sense the current trajectory or the output, compare these two things to see how much far we are from our required output. This is called the error. This error is fed to the controller, and if there is no error, that is, we have achieved what we wanted, the controller will stop working. Otherwise, it will generate some output so that the error can be reduced. Things get complicated when we factor in the robotic manipulator's physical structure. Remember that in the previous video, I explained that the dynamic equation of a robot is in fact a set of n coupled nonlinear second-order differential equations. Therefore, you should appreciate that if we have three connected links in a robotic manipulator, then if only one of them moves, the other two links will feel a change in overall inertia and gravitational forces, which will cause those links to move as well. Therefore, to keep the link stationary, the attached joint should generate some torque to negate the dynamic effect of the moving joint. Now, if we are independently controlling a joint, then how will it compensate for dynamic effects arising because of the movement of other connected links? Well, in this control strategy, dynamic effects of all other links are treated as disturbance, and therefore the disturbance is added into the controller output, and then a disturbed signal is given to the robot. Now the controller has two jobs. First, it should generate outputs such that the robot follows the desired trajectory, and second, it should reject the disturbance arising from the movement of connected links. If the disturbance is of a constant nature, then we can do something about it. But for robotic manipulators, when they are following a varying trajectory, this disturbance is configuration dependent. That is, as the robot is moving, the disturbance keeps on changing because every configuration of the robot is going to have a different dynamical effect on any given joint. Therefore, to tackle this thing, we need to somehow predict the disturbance beforehand. And this is what feed-forward compensator is all about. A feed-forward compensator will somehow predict the disturbance that is going to arise and generate a signal suitable for reducing its effect. When this signal is added into the controller signal, the disturbance can be rejected. So dear learners, this is the overall scheme that we are going to implement in MATLAB for our robotic manipulator. But before implementation, we need to define what this feed-forward compensator is and what this controller is, because there are different techniques to define both of these things. As we are going to discuss PID and PD controller in this video, I'm going to keep the feed-forward compensator quite simple. That is a proportional feed-forward compensator. This compensator just multiplies the reference signal with a constant and add it to the controller output. In fact, it is just amplifying the input signal and nothing else. For the controller, we are going to implement PID and PD controller. Both of these controllers are quite extensively used for robotic applications and have their own advantages. I won't be going into the mathematical details of these controllers as it will be out of the scope of this video series, but I'll just make a comment over here that PD controller is much faster to implement, but may not give complete disturbance rejection and may have steady state error. But this might not be the case every time. Whereas on the other hand, PID controller is a bit more computationally expensive, but has better disturbance rejection qualities and removes steady state error. So what PID or PD controller does is, it amplifies the error by multiplying it with proportional gain, the integral of the error with integral gain, and rate of change of error, that is the derivative of the error with the derivative gain, and adds up all these terms to produce the output. If we have a PD controller, then the integral term is missing. So dear learners, I have tried to very quickly describe the PID controller without going into the details because that will take us away from the topic of this video. So now let's move to the MATLAB Simulink environment and see how we can implement the scheme in MATLAB to control the robot that was not moving on our desired trajectory when we fed it with torques being generated from the inverse dynamics block. So this is the Simulink environment and I have placed few blocks already over here just to save time. This block over here is of signal builder that is creating 3 step signals, and I'm going to provide these step signals as joint angles to the robot. I'm just going to double click on it to see what is happening in the block. So the first signal, which is this one, is nothing but a step signal of 0.2 that is activating at time 0.5 seconds. So I want my first joint to move with a step signal of 0.2 radians at 0.5 seconds time. And then the second signal is activating at 1.5 seconds and it is a step of 0.4 radians. And the last signal, which is the signal for my third joint, it is being activated at time equals to 2 and it has an amplitude of 0.3 radians. These 3 signals are being combined and then are being fed to the scope so that I can view that what is my reference signal. And from these joint signals, I want to generate some torques so that my robot follow these joint angles. And over here we have the same old robot which I have used a number of times. It is nothing but a 3 degree of freedom non-planar manipulator which I have used in the previous videos. And on the output side, I am measuring its positions, its velocities, and joint torques as well. You can turn off these measurements if you wish, but I was using these for some other thing. So that's why these are on, but I have terminated these outputs. So on this side, I am measuring the joint angles on which the robot is moving and then giving it to the scope so that I can compare it with my reference signal, which is coming over here. And this is my measured signal. So that's it. Now we need some kind of a controller over here that will take in the joint angles from this block, produce the torques, and those torques will be fed to the robot. So for this video, we are going to use PID and PD controllers. So let me just place the block over here for the PID controller. And just let me make a point over here that as we want to use a feed forward compensator as well, then in Simulink, we have a 2 degree of freedom PID controller block that implements the feed forward automatically into one single block so that we don't have to route the signal of the feed forward compensator through some other blocks. So I'm going to use a PID controller, but not a simple PID controller, but this one, PID controller with brackets 2 degree of freedom. which means that it will also factor in the feedback and also the feed forward signal. So this is the block which I'm going to use. I'm going to name it as PD1, and I need three of them because I need three PD controllers for three joints. So I'm just going to copy and paste it. So these controllers required a reference signal, which is coming from over here. So I'm just going to connect these ports to these points. Sorry. And then it needs a measured signal, which will be coming from this point. So I'm going to connect this demuxed output to this port. This would be the second joint, and this would be the third joint. Just me rearrange the wires for a bit of clarity. And now these controllers are simply going to generate some output, and that output will be used as the torque. So I'm going to provide these outputs over here. So that's it. That makes our complete block diagram. There's nothing else we have to do. The only thing which we now have to do is we have to configure the PID blocks, and then we have to tune these PID blocks so that they can take in the reference trajectory and generate the required torques. So for that thing, we have to go into these blocks, and over here for the PID controller, we don't need to do anything. But first of all, I'm going to implement a PD controller. So I just need to drop down this menu and select a PD over here. So that's it. And then because we are going to drive a physical model, then keep this thing in mind that always use output saturation. Output saturation means what is the maximum value this controller can generate. Because in simulation, if you are not using output saturation, then the controller might be generating illogical values, illogically huge values to control the robot. And the simulation might be looking very good. But when you try to implement that thing in a physical robot, then in that physical system, it might not be possible for the power supplies or the motors to generate that amount of torque or that amount of power. Therefore, always use output saturation and limit the output so that it can match the whatever you have in the physical hardware. So for example, if you have motors that can generate a torque of 200 Newton meters, a direct drive motor that can generate a torque of maximum torque of 200 Newton meters, then you should limit the output of the controller to 200 Newton meter. Otherwise, whatever is the maximum output you can have, you can enter that value. So right now I'm going to enter 200 over here and minus 200 as the lower limit. Same goes for the other joint controllers as well. So I'm just going to limit those at 200 as well. So now you can see that there is a saturation symbol shown at each of these blocks, at the end of each of these blocks, which means that you have implemented an output saturation. So that's it. We don't need to do anything else. Now comes the a bit of hard part because we need to tune these parameters. Just let me go into this controller once again. You can see over here that we have 1, 2, 3, 4, and 5 variables that needs to be controlled and needs to be tuned. These two constants are PD that are directly related to PD controllers, that is the proportional gain and the derivative gain, whereas these three numbers or these three constants are for the feed forward compensator. So we need to adjust these things or we need to tune these things. The thing with PID auto tuner is that if you have a single input, single output system, then the auto tune function of MATLAB can work very easily and it can easily and automatically tune the controller for you. But as we have a multi-input, multi-output system over here, and we are using, in this case, three different PID blocks, then that automatic tuning won't work over here. So we need to use some kind of optimization method that will automatically tune these things. And for that, we are going to use an optimization function called loop tune of MATLAB. And that loop tune, in fact, uses H infinity optimization technique to figure out all these parameters automatically depending on what cost functions and what requirements you have generated. So I'm going to go through the code and I'm going to teach you that how you can configure this loop tune function and use it to tune all these three blocks. So for that, we have to go to the M file. We have to generate a simple M file that will take in this block, this whole model, and will auto-tune these three PID blocks. So over here, I've already written the code and I'm going to explain it that what this code is. And you can easily copy this code and use it for your program or for your robot. So at the very top, we have to create a tuner interface that will take in the whole function block diagram, and we are going to mark some points so that we can analyze those points later on in our optimization method. So the very first thing is we have to generate this SL tuner, and this SL tuner function will require the model file which we have. So I've named my model file as dof3 underscore rrr underscore pd, and you can see that it is available over here in my working directory. And then we have to name that what blocks we are going to tune. So we have to provide the list over here, and I've generated the list as this PD1, PD2, PD3. And if you remember, these are the three blocks that we are going to tune. So it is the PD1, this one is the PD1, this one PD2, and this one is PD3. Secondly, we have to mark some outputs and inputs and reference signals so that we can later on use these points as analysis points. So for that, we have to use the add point function. And in this tuner, which we have just created over here, we are going to mark the tuned blocks as plant inputs, because whatever these tuned blocks are generating, that will be used as plant input. And the plant output, that is the robot output, that has been marked as the output that we are going to use as plant output. And then the reference signals, we have three reference signals. So I have generated a list over here, and then provided that list to this add point function once again. So right now we have added 3 points. The first point is the controller output that is going to be acting as the plant input, then the plant output, that is the measured joint angles, and then at the end the reference inputs. So we have 3 points which can be used during the optimization method, and we are going to use these points. In the second section of this code, I have used a bit different terminology so that it can better relate with the control system. So I've named the tuned blocks as controls and the robot outputs as measurements. So these are the measurements, that is the robot joint angles, and these are the outputs or the controller output that we are going to feed into the robot. In the third line, I have set some loop tune options because we have to configure the loop tune routine. And in these options, I have configured two things. That is the random start. If you are familiar with optimization method, then you must appreciate that for optimization methods, random starting or the initial point from where you are starting to look for the output or for the answer matters a lot. So we are saying to this optimization method to start randomly at 80 different points. So this loop tune method is going to run 80 different times, and every time it is going to start from a random point. And the second thing is for parallel processing. So if your computer has a GPU, then this function can utilize the GPU and you can run it much faster using parallel function as true. So if you just write true over here, this function is going to use the GPU present in your computer and it will run much faster. But for our case, for this case, where we have only 3 joints and 3 controllers, if you are not using the GPU, then it will be fine. It won't take so long. So I'm not going to use GPU over here. After that, we have to define the tuning goal, that what is the cost function, what are our requirements. For the tuning goal, I'm going to use this function tuning goal, and the tuning goal which I'm going to specify is step tracking. That is, I want to track the step input which I am giving. So the very first input argument is the reference signal, that is the step I'm providing. The second one is the measurement, that is the output of the robot, which we are measuring, the joint angles. And then the third input argument is the tau or the time constant you require. And the last one is the overshoot which this output may have. So I'm not going to discuss that what is this tau or time constant and what is this overshoot. I guess you must be fully aware of what these things are. So I'm going to skip these things. These are the tuning goals that we wish to achieve, and we have configured all other things. Now we have to run the loop tune function, provide it with the initial system that we have, provide it with the controls. These are the controller outputs and the measurements and the tuning goals, and at the end the options which we have configured. So now this function is going to run 80 times because we have used random start of 80, and each time it is going to try to optimize the controls so that the measurements are very much equal to the tuning goal which we have specified. For each of these 80 iterations, this tuning method is going to generate a gain number. That number, if it is equal to 1, it means that we have achieved whatever we wanted in our tuning as our tuning goal. And if that number is away from 1, then that means we are far from achieving the tuning goal. So let's see that what happens and how this optimization method runs and whether it achieves the tuning goals or not. So once this thing is over, whatever is the best possible output or the best possible values of all the variables, using this function, we are going to write the best possible output that we have generated into the Simulink model. So that's it. Now I just need to run it. So before running this thing, make sure that you have loaded the rigid body tree of the robot into the workspace. And after that, we just need to run this thing and we have to wait for the optimization method to complete. Now the optimization method is running and you can see that for every iteration, you are being shown the peak gain. And if this gain is equals to 1, then it means that we have achieved the required tuning goal. But you can see that the minimum this gain is getting is to this 1.2 over here. So let this optimization complete and see that what is the result. So now the optimization has completed and the minimum which we got was 1.8 somewhere. In fact, it was 1.18 somewhere over here. So these values would have been written into the Simulink blocks. So now we have to go to the Simulink block. You can double click on this block and see that what values have been written over here. So now let me run this thing and see that how the robot responds. So the simulation has completed and we can see that how the robot is moving, and you can see that it is quite perfectly moving as far as the visuals are concerned. Now let us examine what is happening in the scope. So in the scope, you can see that this was the first joint trajectory, the yellow one, the blue one was the second joint trajectory, and the red one was the third joint trajectory. And we were providing step signals to these joints, and you can see that how these joints are responding in the real time. If you go into these blocks, then in the second joint controller, you can see that these are the values which are being used for PD, the filter derivative, the filter coefficient, and the set points for the feed forward compensator. And for the third joint, these are the values. Over here, you can see that the PD controller is using quite large values for the PD constants and for the filter coefficients as well. Now, if we use a PID controller, then these values are going to reduce and that will be much more appreciated. So I'm going to change these controllers to PID controllers and make sure that you use a suitable starting point. So I'm going to use the default starting point, which is 1, 1 for the proportional and integral and 0 for the derivative, and 100 for the filter coefficient and 1, 1 for the other two set points. So I'm going to do the same for the other controllers as well. So I've changed all these controllers to PID and let me save it and run the optimization once again. So you can see that after very first random start, we have achieved the target gain of 1 and the optimization has stopped. So now if we can go over here and see that what are the values which are written over here. So these are the values written in the first joint block, these are the values written in the second joint block, and these are the values written in the third joint block. Now you can see that how small these values are as compared to when we were using the PD controller. So let us run it and see what happens to the robot. So in the visual simulation, this is what is happening to the robot. You can see that it is moving quite perfectly. And for the scope, you can see that what is happening over here. So we are achieving a similar kind of response, which is much more closer to the real robot. And you can see that when the second joint start moving, we have some dynamic effect on the third joint and it oscillates a bit, but then it settles and then the things get better. So this PID controller is much more closer to what happens in the real life. But the PD controller was forcing the tuning goal too much by using large gains. So that is not what is desired in real life. So that's it. Now I would recommend the learners to play with this optimization blocks and this whole PID and PD controller and see what other effects and what other goals you can achieve using this optimization method and this kind of techniques. So that's everything for this video, and I hope that you have understood and have learned how to use PID controller and to tune it automatically for a robotic manipulator. In the next video, I'm going to talk about a computer torque controller, and we are going to see that how we can achieve other trajectories using a computer torque controller. One more thing over here I would recommend is that provide a varying trajectory to this robot and see whether this robot is able to achieve that trajectory or not, which won't be an easy task for this controller. So that's all for this video. Thank you and take care.